This new section is entitled Subspaces. First thing we'll do is we will define our subspace. Let V be a vector space with some plus and some dot. If W, which is not the empty set, is a subset of V, and W is a vector space, let me not put it in brackets, using the same plus and minus as V, and W is a vector space using the same circle plus and circle dot as V, then we say that W is a subspace of V. What is going on here? We have this big set V with its two operations, and it's a vector space. Everything inside the circle is part of V, including the subset W. Now W, if using the same plus and the same circle dot as V, if W is a vector space, then we say W is a subspace of V. W is a subset of V. Now notice I never said in the definition that W is a proper subset of V. That is, W might actually be V itself. And the next statement I'm going to say is that a vector space V has at least two subspaces. V is a vector space, then it has at least two subspaces. Has at least two subspaces, namely V itself and the set that just has zero vector. Definitely at least two vector spaces. Let's state this theorem that I'm about to write down and prove it. Very powerful theorem. Let V be a vector space. And W is a subset of V. Now, W is a subspace of V if and only if the following two, we'll call them properties. The following two properties are satisfied. Alpha and beta, the same ones from the definition of a vector space. If U and V are in W, then U plus V must lie in W. And beta, if U is in W and C is any real number, that is a scalar, then CU is in W. And I promise to stop writing circle plus. Now, this is if and only if. So, this part is going to be true for the whole proof. V is a vector space, W is a subset of V. Now, I want to show that W is a subspace of V if and only if these two conditions are met. Okay. So the proof, the first part, going to the right, that is, first we assume W is a subspace of V, and we want to show alpha and beta. Assume W is a subspace of V. Then W is a vector space. So important that I'm going to spell it out. W is a vector space using the same circle plus and circle dot as V. But if W is a vector space, then surely alpha and beta are satisfied. Okay? If W is a vector space, not only do we have alpha and beta, but we have A, B, C, D, E, F, G, and H satisfied. So sure, we have alpha and beta. So that direction was pretty straightforward. Okay, simple is what I'm trying to say. So now let's go in the other direction. The other direction is going to be more tedious. We're going to have to prove A through H just knowing that V is a vector space and that we have alpha and beta. So let me state this, and then I'll draw a little diagram. Okay. Assume alpha and beta are satisfied for W. The closure, the U plus V, is in W. The C times U is in W. Now, back to that original diagram, V and W. Now, if you take two elements in W, say U and V, U and little v, whatever U plus V is, whatever it equals, whatever it is, even if it's in W or not, if you take two elements in W and you add them up, well, these two elements are also in V. So you get something in V. These have to be equal. Because What if you didn't know the elements came from W? What if I erase the set W? There is no W. U plus V in using circle plus and the set V. U plus V is whatever it is. Whatever it is. Maybe it's W. Maybe U plus V is W. Well, just because somebody comes to V, which has a lot of elements, just because somebody comes to V and partitions V, say, you know what, I'm going to call everything in there W. Well, if you're using the same plus in U and V, in set W and the bigger set V, you're going to get the same answer. In other words, 2 and 3, they are integers. And 2 plus 3 equals 5. But Z is a subset of the rational numbers. Well, 2 and 3 are in the rational numbers because 2 can be thought of as 2 over 1 and 3 can be thought of as 6 over 2 or more easily 3 over 1. Well, when you add them, you're going to get the same answer as before. It doesn't matter what the set is. Okay. So keeping in mind that whatever results we get in W is going to be the same as in V, everything's really going to follow from here. Now, the reason we're assuming alpha and beta is because we need it. So in the end, we'll have alpha and beta and A through H. And then we can say that W is a vector space. So all you need for a vector space is alpha and beta. That's what this theorem is saying. All you need for a vector space is alpha and beta. Now, alpha says that U plus V must equal to V plus U. Okay, now we know that if U is in W and V is in W, then the sum is in W. That's what alpha said. That's exactly what alpha said. We are allowed to assume that alpha is correct. Assume alpha and beta are satisfied for W. So if you add two things in W, you're going to end up in W. Now, whether or not these two things are equal, we'll talk about that in a moment. But U plus V and V plus U is in W. So let's write that out. Scratch this for a moment. U plus V and V plus U are in W. This is okay, you know what? Let's write it up very nicely. Let's say that U and V each start off in W. U is in W and V is in W. Let U and V be in W. Then by alpha, we have that U plus V is in W and V plus U is in W. But W is in V. Okay, it's still in V. Hence, U plus V is equal to V plus U. Since V is a vector space. This addition is going on in V. Fair enough. Fair enough. You can say, no, it isn't. It's going on in W. Yeah, but W is in V. the addition. It's the same addition. It's going on in V. Okay, so alpha has been satisfied. Beta. U plus V plus W is equal to U plus V plus W. Okay. This is true since capital V, is a vector space. And I didn't write it, but I should have written let U, V, and W be in W, capital W. So U and V and W are, little w are in the subset capital W. But W's in V. Of course this is true, since V is a vector space. Okay? And this is the tone for all of these. We're going to say that their addition and the scalar multiplication is in V. So whatever properties V has, and the fact that W is closed under scalar multiplication and addition, anything that's true in W, or anything true in V, if it's happening in W, it's going to be true. You add two even rational numbers, you get an even. Well, where do you think those rational numbers came? Those even rational numbers came from? They came from V. Sorry, they came from Z, the integers. Well, here you add two even integers, you get another even integer. Letter C talks about there exists an identity. There exists the zero vector. Okay. Does W have the zero vector? Of course it does. Of course it does. In fact, the reason I just wrote that out was because I wasn't seeing it. But of course it does, because of beta. Let U be in W and 0 be in the real numbers, the number 0. Then 0 times the vector U is the 0 vector which is in W. Why? Because the rule said, letter B says, if you take any vector in W and you scale it, whatever you get, it's in W. So I scaled it with the 0 vector, and I got 0 is in W. Now, I need to show that it has inverses. That W has inverses. Let U be any vector in W. Well then, -1 times U is in W. We proved that in V, -1 times U, if you're in a vector space V, -1 times U is -U. This multiplication was done in V. But since U came from W, and any scalar times a vector from W is in W, whatever this is, namely -U, is in W. And this is for all U in W. So A, B, C, and D are satisfied. Now we go on to the next 4, which talked about scalar multiplication. I'm gonna pretty much say the same thing. Whatever property we have, it's true in V. And since it's closed under dot and plus, since W is closed under dot and plus, we're going to stay in W. It's going to be true in W. C times U plus V. This is letter E, I guess. Okay. Well, we know this is equal to CU plus CV in V. We know that's true. But remember, U and V are in W. But remember, C times U is in W plus C times V. This is in W. Scalar multiplication is closed in W. That's exactly what Bader says. But now we come to alpha. It says when you add two vectors in W, you end in W. Okay. That is, C times U plus V is equal to CU plus CV in W. So that's letter E. Let's see what F looks like. And let's erase this. Letter F, instead of adding two vectors and having one scalar, now we're going to add two scalars and have one vector. It's playing games with us. Letter F goes on to say you have a sum of two scalars and you multiply this by U. U is in W. U is in W. Well, we know that in V that we get CU plus BU. I just want to know, do we get CU plus BU for all vectors U in W? Well, again, a scalar times U, that's in W. A scalar times U, that's in W. For my proof, I would write this. And when you add two vectors in W, you get something in W. This is in W for all U in W. That is, this is true for all U in W. You have to make sure that what you're getting is in W. Just because it's true in V doesn't mean it'll be true in W. Because it is possible, if you didn't have alpha and or beta, this may not be in W. Think about that. It may not be in W. If I let W just be the integers 1 up to 10, okay, well, 8 is in W, 4 is in W, but the sum, and let Z be the bigger set, the integers. When you add these two, you're not in W. You're in Z, but you're not in W. So you have to be careful. And what failed was, I was able to add two things in W and not end up in W. That is, alpha failed. It wasn't closed. Okay, you need to be able to think of examples on your own where you have one set is a subset of another and you don't have closure for the smaller set. The bigger set should be a vector space, but the smaller one should not satisfy alpha or beta. Okay, letter G. G goes on to say if you multiply C times du, you'll get CD times U. C times du is equal to CD times U. Now we know this is true in V. Okay, we know it's true in V. But du is in W. du is in W. C times something in W is in W. So, I mean, you can write this, but du is in W, which implies C times du is in W. So the left side is in W. And CD is some scalar. You multiply two numbers, you get a scalar. And when you multiply that by u, this is in w. So c times du is cd times u for all u in w and, well, not both, since they both equal one another, and cd times u is in w. Okay, now the next and last one, I'll even try to sneak it in here. I want to show that 1 times u is equal to u. Now, this is true in V. If u is in W, then by beta, 1 times u is in W. That is, in W, 1 times u equals u. For all u in W. No matter what u you take in W, 1 times it will equal it. 1 times vector u will equal vector u, and it's in W. You have to make sure it stays in W. So there's a proof of this theorem, and you really can't really understand linear algebra well unless you see the proofs. Okay, when there's too much memorization going on in mathematics, and that's why students have the hardest time doing math. You can't memorize everything. And even if you could, you most probably forget it rather quickly. For most of us, especially me, can only memorize things for short lengths of time. You have photographic memory, that's a whole nother story. But that still doesn't mean you understand it. Alright. Suppose we take W to be this set. W is the set of 3 by 3 matrices where you must have zeros in those two positions. This is in set of matrices that are 2 by 3s, such that A, not A, scratch A please, B, C, D, and E are real numbers. Okay, all these numbers are real. B, C, D, and E. So we want to prove or disprove that W is a subspace of none other than M23. M23 is a subspace. Sorry, W is a subspace of M23. Okay. A couple of things I don't know why it looks like it says is not a subset, is not an element of. So let's rewrite it. This is an element of M23. Okay, so now what I need to do is show that if I have to show alpha and beta. Let 0 be C, D, E 0, and 0 B prime, C prime, D prime, E prime, and 0 be in W. I want to show that when I add them up, I get something in W. Now, how do you get something in W? Well, you have to be 2 by 3, and you have to have zeros in those two positions. And the other positions are real numbers. Okay, so I add these two. I add them. This matrix, using, okay, Is W a subspace of M23 using regular plus and regular circle dot? That is regular matrix addition and regular scalar multiplication by a matrix. So I add these two, and sure, it's going to work out nice and smoothly. 0 plus 0 is 0. B is a real number. B prime is a real number. So when I add those two, I get a real number. C plus C prime is a real number. I get B plus B prime, E plus E prime, and 0 plus 0. I got my necessary zeros, so I am in W. The alpha has been met. That's alpha. Now I'm going to try beta. I won't say C is a scalar because I'm already going to use C. Let R be a scalar. When I multiply R by this matrix right here, and it's regular scalar multiplication, that's the decrease, I get R times 0, which is 0. R times B is a real number. R times C is a real number. R times D is a real number. R times E is a real number. R times 0 is the real number 0. Yeah, look at this. I got back in W. These 4 entries are real numbers, and those 2 entries are the number 0. Okay? Therefore, W is a subspace of M23. It really is. I proved it using that nice theorem. Theorem really cuts down on things. You don't have to. Now you could, if you want, using the same plus and dot as V. You can show that W is a vector space by showing all 10 properties. You can show all 10 properties. But you only, and then you would be 100% right that W is a vector space. Since W is a vector space using the same operations as V, and W is a subset of V, you got it. You can now say W is a subspace. But why show all 10? Why show A through H when you don't have to? Now, we can even make that last theorem shorter. We can even make the last theorem shorter. We won't prove this one, but maybe you can do it for exercise, as an exercise. Let W, which is not empty, be a subset of V, a vector space. V is a vector space. Then, W is a subspace of V if and only if A times U plus B times V is in W, where U and V are in W, those vectors are in W. So if you take any 2 vectors in W, arbitrary any 2, and you take a linear combination of them, and you still end up in W, you got it. And A and B are real numbers. Actually, maybe I will prove this one. Maybe I will prove this. So, W is a subspace of V if and only if this is in W. And we're allowed to say that W is a non-empty subset of V, and V is a vector space. V is a vector space. So let's go to the right. W is a subspace of V. W is a subspace of V. That is W is a vector space. W is a vector space. Okay. If U and V are in W, then A times U plus B times V is in W. Okay, now why is that? That's obviously true. Because if U is in W and W is a vector space, then any scalar times U is in W. This is in W. V is in W, or scalar times V is in W. You add two things in the vector space W, you end up in W. So that one was straightforward. Now I need to show if this is true, then W is a subspace of V. But I'm not going to go through those 10 definitions. I know how to show something is a subspace of V. In other words, this statement, W is a subspace of V, is the same as alpha and beta are satisfied. The same as alpha and beta are satisfied. Okay, so we need to prove that. We want to show that alpha is true. Now we know that, okay, so assume AU plus BV is in W for all U and V in W, and for all A and B in the real numbers. So now, I need to show that U plus V is in W. Okay. Let A equal B equal 1. 1 times U plus B times V. 1 times U is U. 1 times V. 1 times V is V. So V plus U plus V is in W. Because this is in W. That's in W. Nobody says the scalars can't be any scalar. Yeah, it's for all A and B. Okay, now for beta, I want to show that a multiple of U is in W. Well, I know that any multiple of U plus any multiple of V is in W. So I'll take 1 times U plus 0 times V plus 0 times V. Well, this is 0 and this is U. U plus the 0 vector is U. This is in U. But this is in W. A number times U plus a number times V, that's what we're assuming. This is in W. Oops, I do have one slight error. I want a general coefficient, a general scalar. And now I have any multiple of U is in W, and this is for all U in W. Okay, I showed that AU is in W. That's all I needed to show. For any A and any U, for all U in W and C in the reals. Any, well, I called CA. and for any real number A. And that's all I wanted to show, that A times U is in W. For any U in the W and for any scalar. So that's proof. So now, instead of doing the two-step process that the last theorem said, we just have to show that AU plus BV is in W. Not just for two concrete U and V, but for any U and V. So that's a very nice theorem. Now we go on to this example. Let us consider this example. Let me erase the board first. Now, we let W be the set of elements or vectors 1, B, C, which is in R3, where B and C are real numbers. B and C are real numbers. Now, this is a subset of R3. The first, and what makes it not equal to R3, and I didn't say that. I said it's a subset of R3. It might even be equal. It is not equal because in R3, the first number doesn't have to be 1. Okay, we're making the first number 1. Okay. Is W a subspace of R3? Now remember, before W can be a subspace of this set, that set has to be a vector space. And we know that R to any n, R to the 1, R to the 2, R to the 3, R to the 99, that's a vector space. So is this a vector space? And I hope you realize the answer is immediately no, because alpha is not going to be satisfied. If you take two such vectors, and you can even give them real numbers. If you take two of these objects in W, 1, B prime, C prime being the second one, and remember the first entry has to be 1, and the last two can be whatever you want. The thing is, when you add them, 1 plus 1 is no longer 1, it's 2. So no, it's not going to work. This is not an element of W. When you add these, and again, to show counterexamples, you can use real numbers. You can use a concrete example. Okay, this is not in W. That is plus or not close. Alpha is not satisfied. Alpha is not satisfied. W is not a subspace of R3. You don't need this. You could have, instead of this example in the bottom, you could have put it right here. You could have put it right there. And then you say alpha is not satisfied. I took two vectors in W and I added them together and I didn't get something in W. After all, it says for any U and V in W, U plus V must be in W. Well, I took two real live elements in W, and I showed that when I added them, I didn't end up in W. Why is that not good enough to prove? Suppose those two examples that I picked from W, they do land in W when you add them. Well, is that enough to show that any U plus V in W, any U and V in W, when you add them, it ends up in W? No, not at all. There might be just even one example of a U and a V where when you add them, you don't end up in W. Well, that's enough. That's enough. Okay. How about this example? Is this set going to be a subspace of another set? Let V be the set of all polynomials of degree 3. Okay. Clearly, V is a subset of P3. Remember, P3 is the set of all polynomials of degree 3 or less. Our V does not equal to P3. V says to be in V, to hang out with V, to be a member of V, you have to be a polynomial of degree 3. The degree of this polynomial is 2. Since it's 3 or less, it's a member of P3. An element of P3, but it's not an element of V. To be in V, your degree must be 3. If I added on 7x cubed, fair enough, it's in V. Okay. So the question is V a subspace of P3? The answer is absolutely no, because think about it. If you add two polynomials, I'm going to put a 3 there. If you add two polynomials in degree 3 together, x squared. If you add two polynomials of degree 3, do you have to get a polynomial of degree 3? The answer is no. When you add 8x cubed and negative 8x cubed, you get 0. And when you add 2x cubed and 2x squared, when you add it to 5x squared, you get 7x squared. Negative 2x plus 4x is positive 2x. 1 plus 2 is 3. This is not in V. Oh, by the way, I didn't say it. I really should. Regular plus and regular scalar multiplication. It's not in V. Okay? So here's enough for you to be able to now say V is not a subspace of V. V is not a subspace of V. Let me just erase this, please. Oops. Of P3. Of P3. V is not a subspace of P3. Now, the reason I put this all the way on the bottom is because I'm going to show you another way where you could have concluded that. If you didn't want to use this example right here. If you didn't want to use that example, you could have said, well, here is a polynomial in V. Here's a polynomial in V. The coefficient of x squared is 0. Here's a polynomial of degree 3. And no matter what I scale it by, it's supposed to end up in P3, or end up in V, excuse me. It's supposed to end up in V. Well, this is the 0 polynomial. 0 times that is 0, plus 0 times that is 0. You add up 0 times 1 is 0. You add or subtract those zeros, you get 0, which is not in V. Which is not in V. But this violates beta. So V is not a subspace of P3. This up here violates alpha. So V look like a P. V is not a subspace of P3. V is not a subspace of P3. You could have given the top counter example or this bottom counter example. If W fails to be a subspace of the vector space V, it is not necessarily true that both alpha and beta fails. You can have one fail and not the other, or you can have both of them fail. You have regular addition and bizarre scalar multiplication. Well, it might pass addition. But the scalar multiplication might fall apart. And now here's a very interesting type of problem to think about. Back to matrices and homogeneous systems of equations. Consider the homogeneous system AX equal to 0, where A is an M by N matrix. Now, what kind of space is X in? Is it Rn or Rm? Well, A is M rows, C columns. So, you have A11, A12, C columns, N columns, excuse me. So you end up A1N. And then A21, A22, all the way up to A2N. Well, what are you going to have to multiply this by? Remember, you're going to dot this row with this column. You're going to have the same number of elements, same number of entries. Well, we can count. That's the first entry. That's the second entry. Oh, look, that's the nth entry. That is, we better have something in Rn. And this is true for every row. Every row has 1, 2, n entries. So this vector on the right must live in Rn. Is the set of all solutions to AX equal to 0 a subspace of Rn. All the solutions come from Rn. All the solutions are x's. What can x equal? Okay. So let's verify Let's try to use the new theorem. Let's use the new theorem. Okay. Solution. Let x and y be two solutions to ax equals 0. And a and b are any real numbers, scalars. So I need to show, okay, that is ax plus by. Let's just give the set of solutions a name. Let G equal the set of all solutions to ax equals 0. Okay? So is ax plus by a solution? That is it in G? And I don't know why I chose G. I've been using W. Well, this is the solution if and only if a times it is the 0 vector. Now, we know, now, this is a vector, and this is a vector, and a times x is a vector, b times y is a vector. We can think of this as b, and this as c. We know that a times b plus c is ab plus ac. That is, matrices have the distributive property over addition. So this is a times ax plus a times by. We also know that if you have a times a scalar times b, you can bring the scalar in front. This is a times ax. The b can come in front, plus b times ay. And here's where it comes together. This is a times 0, because ax is 0. Okay, because we said x and y are solutions. So b times ay is 0. A times 0 is a 0 vector. A scalar times a 0 vector is a 0 vector. You add them, you get the 0 vector. Okay? And you just write up that you're done now. Just write up what you can you're allowed to conclude. To mark it down before I try to erase. Okay. So now, since the arbitrary ax plus by is in G, we can now say that G is a subspace of Rn. G is a subspace of Rn. This is a one-step proof, which is pretty cool. You don't have to bother to show alpha and beta separately. This theorem that we just used, it really combines showing alpha and beta is valid with just 2 steps. Sorry, with 1 step. 1 step is always better than 2 steps. Besides, we should be able to use either of the 2 proofs. Either of the 2 theorems, excuse me. The one that says W is the non-empty set W is a subspace of vector space V if and only if alpha and beta are satisfied. And the other one that says if the non-empty set W is a subset of the vector space V if and only if A times U plus B times V is in W. The next thing we're going to talk about is something interesting. I was wondering where my professor was going to go with after this one. Let U and V be in V. V is a vector space. So we take two elements of a vector space. Show that the set of all linear combinations of V1 and V2 is a subspace of V. Okay, so here's a way to generate subspaces. Take any two elements in a vector space V, and then show that the set W of all linear combinations. So let W be the set of all linear combinations of any two vectors in V, vector space V, and I claim that that new set is a vector space. Now, to prove this, is W a subset of V? The answer is yes. If you take two vectors in V and you take linear combination of them, you're still in V. Okay? And if you're, so again, we're taking them from a smaller segment of V. This is V. You take any two elements of V, a linear combination still lives in V. If V has more vectors and W is just part of those vectors, well then, yeah, if you add a linear combination of these vectors in V, it's still in V. Okay, W is a subset of V. Actually, this is not W. I'm sorry. This is not W. You have a set, a subset of V, and you consider all linear combinations of that. The set of all linear combination of these four elements. That's W. This set might just be U. W is in V since V has alpha and beta. Depending upon your teacher, he or she may want you to show that W is in V more rigorously. But for a student at your level, it will be pretty good just to even realize that that's an issue. Pretty good just to say, yep, that's an issue. W is a subset of V since V has property alpha and beta. Okay. So now, why is W a subspace? Well, let U be in W and V be in W. So if U is in W, U is A times V1 plus B times V2. And little v is in W, little v is in W, so V is out in the A prime V1 plus a multiple B prime of V2. Now, u plus v is simply AV1 plus BV2, that's u, plus v, which is A prime V1 plus B prime V2. But this is adding these two first, because vectors have the commutative and associative law. That is, you can add in any order. This is A plus A prime times V1 plus B prime times V2. This is a real number times V1 plus a real number times V2. Well, that's exactly how you get to B and W. Your linear combination of V1 and V2. And now, so that's alpha. Now we need to show beta. Okay, I need to show that. So let that still be u. I need to show that C times u, which is C times AV1 plus BV2, this is CA times V1, that you can distribute and factor out the scalar, plus CB times V2. Well, that's in W. That's exactly how you get to B in W. Your scalar times V1 plus the scalar times V2. Therefore, W is a subspace of, so let me see what we called it. V is a subspace of V. Okay, so if you have a vector space that has even just one element, a linear combination of that one element, that is, scalars of that, instead of all scalars of that vector, is a vector space. So if you have two distinct vectors, well then any linear combination of those two vectors will form a vector space. If you have a vector space V and you take three elements from V and you form all the linear combinations of those three vectors, that new set, the one that has the linear combination of all three of these vectors, all linear combinations, it will be a subspace of the vector space V. Okay, so let's talk a little bit more about linear combinations. Let V contain the vectors V1, V2, V3, all the way up to V sub k. Well, let me not say that, I'm sorry. Let this set be a subset of V, where V is a vector space. So we took some vectors from V. We took some vectors from V, the vector space V. Maybe we took a few, maybe we took most, maybe we took all of them. But nonetheless, it is a subset of V. A vector V is a linear combination of the vectors, let's name this set S. So a vector V is a linear combination of the vectors in S if little v is a linear combination of the vectors in S. That is, it's a multiple of C1 plus a multiple of V1, plus a multiple of V2, all the way down to a multiple of Vk. Okay. Now you may say, but wait a minute, why should all these scalars be the same? Yep, you're right, they shouldn't be. Now I have two options. I can call it CV1 plus VV2 plus EV3. Oh my, what is K gonna be? Well, you need to think that, what if K is more than 26? So you can't even use A through Z. I mean, I could have called this A, and this B, and this C, and the next one will be D. But why not C1, C2? Oh, look at that. The subscripts match. Oh, that's going to be C sub K. Any one of those C. First, let me say what the C's are. The C's are real numbers. The C's are the scalars. They're real numbers. Where C1, C2, etc. up to CK are all in the real numbers. Okay. And I was about to say where any one of these could be 0. In fact, if V is the 0 vector, well then let all the C sub i's be 0. C1 is 0, C2 is 0, they're all 0. Well, of course, 0 times V1 is the 0 vector. 0 times V2 is the 0 vector. They're all 0 vectors. You add them up, and you get the 0 vector. Okay, so they can actually all be zeros. That's a linear combination. You have a set of vectors, and you take a linear combination of them. A multiple of the first vector plus a multiple of the second vector plus a multiple of the third vector, etc. That sum will be a linear combination of the vectors. Now, sometimes you could you'll get a result. And well, let me rephrase it as just a problem. Let me just rephrase this as a problem. Let V1 be the vector 1, 0, 0. V2 be the vector 3, 0, 2. And V3 is going to be the vector 1, 2, 0. Let V1, V2, and V3 be in R3. So we want to show the following. Show that, let's call the vector V. Let me rewrite it. Show that the vector I'm about to write is a linear combination of V1, V2, V3. Show that the vector V equals, say, 7, 6, 4 is a linear combination of the vectors V1, V2, V3. V1, V2, and V3. That is, this vector V can be written as a multiple of vector 1 plus a multiple of vector number 2 plus a multiple of the vector V3. Now, you can be clever in how you do this. Sometimes you don't have to do things in a mechanical way. Sometimes you can do something by thinking. I noticed that the only vector that touches the middle term is this vector. And since I want a 6 in the middle term, I'm going to put a 3 there. Because no matter what number I put here, when you multiply it by 0, it'll be 0. Whatever number I put here, you multiply it by 0, you get 0. And 3 times this is 6. Well, 0 plus 0 plus 6 is 6. I'm guaranteed I'll get a 6 in that position. And it's the only way I get a 6. Okay? Now, this here, this vector, is the only, so right now, I have 3, 6, 0. That's what I have so far. That is 3 times this vector is 3, 6, 0. In fact, let me put it closer to the left, and we'll do bookkeeping. 3, 6, 0. Now, this middle vector is the only one that touches the last digit, because the other two vectors have a 0 there. Well, I want a 4. Oh, okay. 2 times 2 is 4. 2 times 2 is 4. Now, 2 times this vector is 2 times 3, 2 times 0, 2 times 2, which is 4. Now, I ultimately want 7, 6, 4. Now, this first vector does not touch the second and the third position. That is, I have a 6 and a 4. But I have a 9 here so far. I want to get 7. So I need a negative 2 to be there. Well, if that's 1, I'll multiply by negative 2. And I'll get negative 2, 0, 0. And now when I add these up, I get 7, 6, 4. So I did write the vector v as a linear combination of v1, v2, v3. Now, if you hated thinking, which you really, really shouldn't, makes it more fun. But if you really don't like thinking, we have to deal with matrices. Think and system of equations and all that fun stuff. Okay, this first alpha times the first vector is alpha 0, 0 plus 3 beta, 0, and 2 beta. And 1 times gamma, 2 times gamma, 0 times gamma. You add the first components, you get 1 alpha plus 3 beta plus 1 gamma must equal to 7. And then I'll even call these alphas. No, this I'll call beta and gamma. You have 0 beta. No, why am I confused? I'll still call them alpha. 0 alpha, 0 alpha, 0 beta, and in the last entry is 0 beta. So the second entry tells me 0 alpha plus 0 beta plus the last one, that last 0 should be 0 gamma. 0 gamma. Okay, so I have 0 alpha plus 0 beta plus 2 gamma plus 2 gamma, and this should equal to the second entry, which is 6. And then I have 0 alpha plus 2 beta plus 0 gamma, and this should equal to 4. So now I have my system of equations. I can solve it. And by the time I just got the system of equations, I could have done 2 of these type problems in my head, if they were as friendly as the one that I just did. Okay, so we need to solve the system of equations on the bottom, and we're going to come up with the same alpha, beta, and gamma as we did a few moments ago. the one we got by thinking. Keep in mind that there's an understood 1 alpha, 1 gamma. So I write down the coefficient matrix. That is, I write down the first column of numbers, 1, 0, 0. I write down the second column of numbers, 3, 0, 2. I write down the third column of numbers, 1, 2, 0. And it's augmented with the other side of the equal sign. That is 7, 6, 4. Okay. I will divide row 2 by 2 and row 3 by 2. So row 1 did not change. Row 2 becomes 0, 0, 1, 3. Row 3 becomes this. Okay. Column 1 is fine. Here's my leading entry. What's below it is zeros. I'll move that into column 2 in a moment. That is, I'll interchange 2 and 3. But let's kill off that 3. Let's just do row 1, which has this 3 here, and I'll take away 3 times row 3, which will put us 3 there. This is row 1. This here is 3 times row 3. If I subtract, I get that. Okay, and I'll also interchange row 2 with row 3. If I have the new row 1, it's at the bottom right. It's 1, 0, 1, 1. Row 3 goes next, and row 2 goes next, goes last. Okay, and now all I have to do is get rid of that entry by doing row 1 minus row 3. Yes, I'm going a bit fast on the reduction because we should be experts on this now. If you do row 1 minus row 3, you get this and a negative 2. And row 2 is fine. Row 3 is fine. The first row says that 1 alpha is equal to negative 2. 1 beta is equal to positive 2. And gamma is equal to 3. The same answers we got before. So now you have to say is that vector v, 7, 6, 4, is equal to negative 2 times v1 plus 2 times v2 plus 3 times v3. Because that was the problem. Don't do all the work and not answer the question. Write 7, 6, 4 as a linear combination of v1, v2, and v3. Now, let's talk about what it means, or you have a set V, and you want to talk about all linear combinations on the set V. Well, what do we call this new set? The set that contains all linear combinations of the set V. Let me erase the board and then I'll write down what we call this new set. Because if you take linear combinations of vectors, you get new vectors. And when you put all these vectors together, you get something called a set. So let S equal V1, V2, all the way up to Vk. Let S be a set of vectors in the vector space V. So all those vectors are in V. Those vectors might make up all of V. that is set S equals V, or set S is a proper subset of V. That is, every vector in S is in V, and V has other vectors as well. Okay. The set of vectors in V which are obtainable from linear combination of the set of all vectors in V, which are obtainable from linear combination of vectors in S, is called the following. It's called the span of S. Of course, another way of writing S is this way. What does span of S mean again? It's the set of all linear combinations from those vectors. And when you take a linear combination of those vectors, you get another vector. It's the set of all of those vectors. The set of all of those vectors that came from linear combination of all of these. Well, my question is V2 in the span of S? Is V2 an element of the span of S? The answer is yes. Yes. Since V2, and I'm not saying this definition is unique, but I can say that V2 is 0 times V1 plus 1 times V2 plus no times V3 all the way down to no times Vk. That is, with the exception of V2, I keep adding the 0 vector. The 0 vector plus the 0 vector plus the 0 vector plus the 0 vector is the 0 vector. And 1 times V2 is V2. And the 0 vector plus V2 is V2. Okay, so everything in S is in the span. I won't prove this, but that's the gist of the proof I'm about to state. The theorem is that S is a subset of the span of S. Every element in here is in the span of S. Okay? Now, if V sub k is in here. Well, here's the proof. V sub k, that's in S. This is equal to 0 times V1 all the way up to 1 times Vk, and then I start again with the zeros. Because 0 times, I shouldn't have said Vk. Somewhere in there is V sub r. V sub r is somewhere in there. Because the last one is Vk. So somewhere in the middle, I just take 1 times Vr, which is Vr. This is 0, all of these are 0, and all of those are the 0 vectors. You add all those 0 vectors, you get the 0 vector. That's 1 Vr is just Vr. You have the 0 vector a lot of times, and then Vr, and then the 0 vector a lot of times. That's Vr. That's Vr. Okay. So every vector in S is in the span of S. Now you might be able to get Vr. You know, what if V sub r equal to 3V1 plus 4V2? So then I can just say 3 times V1 plus 4 times V2 plus 0 times V3 plus 0 times V4 all the way down to 0 times Vn. Notice I didn't have to say 1 times Vr. But that's not always true. Vr does not always equal 3 times V1 plus 4 times V2. So I'm going to give you a set S and ask you what the span is. Suppose S is the set of these vectors. Sorry. They're vectors, but let's say matrices. What is the span of these, I guess, 4 matrices? What is the span of these 4 matrices? What is the span of this? Well, how do you get into the span of S? You take a multiple of the first matrix or vector plus a multiple of the second one plus a multiple of the third one, an arbitrary multiple of all of them, including the last one. Okay? Well, this gives you A00000 plus the next one is 00B000 plus 000C00 plus 00000D. Now, when you add these up, you will get, you add the first, the 1, 1 position, you get A. You add the 1, 2 positions, you get 0. You add the 1, 3 position, you only get B. In the bottom, you only get C. And you add all these 4 zeros, you get 0, and then D. That's the span. That is, you get a 2 by 3 matrix where those 2 middle ones are 0. The span of S is the set of all matrices of this form. A, 0B, C, 0D, and okay, such that A, B, C, D are real numbers. That's the span. Okay. If you want, you can say these are elements in M, 2 rows, 3 columns. But that's not necessary. Okay, so that's the span of S. Nothing major there. Take a linear combination of the vectors, arbitrary linear combination. Add them up, and then whatever you get, that's what the span is going to be. Now, it's not, you might be able to clean up that answer in the end. In other words, if V1 is 0, 0, 4, and V2 is 0, 0, 7, and V3 is 0, 0, 8, now I'm hoping you would see the span of this. But for now, so you have A times V1 plus B times V2 plus C times V3. That's that is 0, 0 for A plus 0, 0, 7B plus 0, 0, 8C. I think gammas there represent C. Now, if you were to add these up, you get 0, 0, and plus 0 plus 0 plus 0 is 0. 0 plus 0 plus 0 is still 0. The third component is more complicated. It's that. Okay, now, it's not wrong. I would hate not marking this wrong, but I have, or maybe I said that wrong. I would hate marking this correct, but I have no choice but to say that that last line, yeah, that is the span. The span of V1, V2, V3 is this. But since alpha and beta and gamma can be anything, why not just call this, I don't know, lambda? Call it lambda. That is, the first two entries must be 0. The third entry can be anything. So that's what I meant by cleaning up. Once you take a linear combination of the three vectors and you get something like this, just clean this up. If you said the span of V1, V2, V3 equal this, it would not be marked wrong, or it shouldn't be marked wrong. Okay, because it's not wrong. 4 alpha plus 7 beta plus 8 gamma is any old number like lambda. Okay. Let's do one that, well, let's state this theorem. This theorem is important to know. Now, this is just a generalization of what we said earlier. We said earlier, if you take two vectors from a vector space, then any linear combination of those two vectors, the set of all linear combination of those two vectors, which now we know is called the span of those two vectors, is a vector space. Now we're just going to generalize it. There. Let S equal to V1, V2, up to Vn be a subset of V. V is a vector space. Then the span of S is a subspace. The subspace of V. So this is the set V, and it has many vectors in it. And you take those four vectors, V diagonal. You have the set V. Now, this, remember, V is closed, so linear combination of vectors in this set are still in that set, in the set V. Now, if you take the span of V, sorry, give me one moment, please. Here are those four elements. If you take the span of these four, you're going to probably get an even bigger set. We'll call this set S. That set is the span of S. Okay? The theorem is saying that this set, the span of S, is a subspace of the vector space. You have lots of things going on. They're all exciting. And you have to start making the connections. I made all these connections a year after I took the course. A year later, I just woke up one day and everything that confused me was no longer confusing me. So how about we consider this column? Let V1 equal 3t squared minus t plus 3. V2 is t squared, say minus 5t. And V3, how about 4t squared minus 4t plus 7. And V3 will be 2t squared minus 4. Okay, so let these vectors be in P3. So all degree 3 or below. Now the question is this vector u, that is t squared plus t plus 1, in the span of V1, V2, V3, and that last one should be called V4. So what we're asking is u t squared plus t plus 1 a linear combination of the 4 vectors, v1 through v4? Due to space, let me move this over a little bit. Space constraints. T squared plus t plus 1. Is it a multiple of v1? Is it a multiple of this? Plus another multiple of v2. Plus a multiple of v3. 4t squared minus 4t plus 7. Plus a multiple of v4. 2t squared minus 4. T squared plus t plus 1. Let's get the t squares together. We have 3 alpha plus beta plus 4 gamma plus 2 lambda t squares. How many t's do we have? Well, we have minus alpha, minus 5 beta, minus 4 gamma, and that's it. That's t squares. Lambda, there are no t squares in x of 4. And the constants. We have plus 3 alpha, no constant here, plus 7 gamma, minus 4 lambda. This here must be 1. Just like on the left we have 1 t squared. Plus, this must also be 1. Because this only has 1 t. And coincidentally, this is also 1. Because that's the constant. I equated coefficients. The coefficients of the t squares have to be the same. Whatever this is, it must be 1. Whatever the coefficient of t is, that is, whatever this is, it must be 1. The constant must equal a constant. Okay, so we have that 3 alpha plus 1 beta plus 4 gamma plus 2 lambda must equal 1. And this is also 1. Negative 1 alpha minus 5 beta minus 4 gamma plus 0 lambda. The last one, the constant, 3 alpha plus no betas plus 7 gammas minus 4 lambdas must equal to 1. Now, the question is U in the span? They never said define the linear combinations. They never really said find alpha, beta, gamma, and lambda. If we did, then yeah, it'll be in the span. The question is, are there going to be an alpha, beta, gamma, etc.? I guess I should have used delta. Are there going to be is there going to be a solution? In fact, there might be infinitely many solutions. Now, this is where you have to put all the ideas together. You have to put all the ideas together. Is this going to have a solution? Is this going to have a solution? That is if I write down the coefficient matrix, 1, negative 5, 0, 2, 0, negative 4, 1, 1, 1. Is this going to have a solution? Okay, now, if the determinant is 0, something happens. If the determinant is not 0, something happens. And that's where you need to have these ideas in your head. You need to have all of this in your head. Okay? So let's talk about this for a moment. If I say that, now if I call that A, when I multiply it by X, I want to get B. Now, I'm guaranteed to find an X if A has an inverse. Because then X would just be A inverse B. Now, okay, so we could just take the determinant of this. We could just take the determinant of this. And I love that 3 there, because it's the same as that 3. I'm going to subtract those 2 rows. 3 minus 3 is 0. 0 minus 1 is minus 1. And negative 4 minus 2 is negative 6. Okay. I'm not exactly sure why I did that, but I did. In fact, let me add those 2 rows and put it on the bottom. I'll change that number in a moment. Now, we don't want to add those 2 rows, because then the bottom left entry will no longer be 0. So we'll just do the spaghetti method here. We have an extra 0 in the bottom left. 3, negative 1, 0, 1, negative 5, negative 1. This turns out to be 90 plus 0 minus 2. 90 minus 2 plus. This is 0, this is 0, and this is 6. Oops, that should be minus. I know one thing, this isn't 0. 88 minus 6 is 82. This is not the number 0. This is not the number 0. Okay? So that implies A has N. inverse, which implies x is a unique solution. That is, we got a solution. I don't care if it's unique or not. We got a solution. We got a solution, which implies that t squared plus t plus 1 is in the span of S. Now, I will confess, while I was doing this, I knew that either the determinant of A will not be 0, or the determinant of A is 0. Okay? Now, if the determinant of A is 0, I thought, well then, we'll have an infinite number of solutions. That is, we have a row of zeros. And I'm like, well, either way, we have solutions. But then I know some problems have no solutions. What would have happened would have been something like this. If you reduce this matrix, and I don't know, maybe you get something like this, with a row of zeros. If this were 0 here, then there'll be, and I don't care what's here. If this was 0 here, then yeah, you would have gotten an infinite number of solutions. But if it was an 8 here, and still this determinant is 0. If you had anything but a 0 here, then there would have been no solution. And then you would say, no, this vector u is not. This vector or polynomial is not in this span of S. Okay? So nobody says you had to actually find out the alpha, beta, the gamma, and the lambda. You didn't have to. You just had to give a good enough argument where you can say, yeah, of course it's in the span. Okay, now on to some theoretical exercises. There's a number of nice ones in this section. Now, I do want to comment on one thing. Taking the determinant of A in this last problem was a little bit dangerous. Dangerous meaning maybe it wouldn't have helped. That is, if we would have taken the determinant of A and we did get 0, well then I had to actually go back and row reduce to find out if we had infinitely many solutions or none. Okay. We want to show that AX equals B, where B is not 0, where, say, A is n by n, is not a subspace of R to the n. It is not a subspace of R to the n. The reason is, since B is not 0, B plus B does not equal B. Okay? Proof. If I can call it a proof. Let x1 and x2 be two solutions to AX equals B. Okay? Right? So then their sum should be a solution to be a subspace. A times x1 plus x2 is, matrices have that property. It's A times matrix A times the matrix x1 plus matrix A times the matrix x2. But this is B and this is B. Oh, this is 2B. It's not B. So then, x1 plus x2 is not a solution. That is, the set of solutions to AX equals B is not a subspace. In this case of R sub n. It's not a subspace. This didn't work out. It could have, but it didn't. Okay. Remember, the set of solutions to AX equals 0, that's called the null space of A. What do you multiply A by to get 0? It's a 0 vector. If A is non-singular, then what's the null space of A? If A is non-singular, then describe the null space of A. Okay, well, A non-singular implies A inverse exists. AX equals 0 on each side of the equation. On the left side, I'm going to multiply by A inverse. Matrix has associative law. Matrix multiplication has associative law. This is I times X, that's X. And any matrix times the 0 vector is the 0 vector. Okay, so 0 is the only vector in the null space. The null space of A is equal to just the 0 vector. It could have been others, but not in this case. The only time you're going to have others if A is not non-singular. That is, A is singular. A has no inverse. Okay, let's consider the next one. We talked about this one. Oh, we said, I mentioned if V just had one element. But what if V has many elements and we pick one of them? And we consider multiples, scalar multiples of this one element of V. I claim that this new set, the set of all multiples of this one vector in V, is a subspace. So here it goes. Let x0 be a fixed vector in the vector space V. Okay, so we have one vector. We pick one vector from V. Now I claim that the set W is the subspace of V, where W is equal to the set of all scalars times x0, where C is a scalar. I let W equal that. I claim W is a subspace of V. So I want to show that a linear combination of two vectors, two arbitrary vectors in W is still in W. Okay, so let W1, which is C1 times x0, and W2, which is C2 times x0, those are two arbitrary elements in W, because x0 can't change. The scalar can change. Then, so let's do the single one. Alpha W1 plus beta W2. Okay, alpha times W1 is C1x0 plus beta times W2 is C2x0. So then this is alpha C1 times the vector. The scalar can come in front, plus the scalar can come in front. So beta C2 times x0. Well, I can factor out the x0. This is alpha C1 plus beta C2, which is a scalar, times x0. Call this lambda. This is equal to lambda times x0, which is in W. So, W is a subspace of V. So there's the easiest way of finding a subspace. Take any element of V, of a vector space V. Very easy to find a subspace of the vector space V. Take one element in V and consider all multiples of it. That would be a vector space. Okay, let's try the next and last one. Let W1 and W2 be two subspaces of the vector space V. So let's define the set W1 plus W2 to be the set of all vectors V in the vector space such that V is a sum of two vectors, one from W1 and one plus W2. Little W1 plus little W2. Where little W1 comes from W1 and little W2 comes from W2. So let's make these W's bigger. Big W1. Big. The vector spaces are always big. We have vector space V, and we have V as an element, little v. Even if I wrote little v that way, little v is an element of the vector space. It belongs to, it is in the vector space. Okay. So, of course, we want to show that this set, show that W1 plus W2 is a subspace of V, subspace V, vector space V. Okay, so we'll use the one-step theorem. So please don't get caught up with a name of a vector. I don't care if it has a plus in its name. It's a vector space. So basically we're going to say let U and V be in W1 plus W2. And I want to show that A times U plus B times V is in W. Big W. Okay? And once I show that this is in W, we're done. Now, how did U get to be in here? U must equal to, say, A times W1 plus B times little w2. That's how you come to be into W1 plus W2. You're a multiple of something in W1 plus a multiple of something in W2. And V is a multiple of W1 plus a multiple of W2. Just for the record, W1 is in W. The reason is, to be in W, if U is in W1 plus W2, that means that U is a multiple of a vector in W1 plus a multiple of a vector in W2. But if B is 0, then you have AW1 plus 0 W2. That is, you have AW1 plus 0, which is AW1, which is in W1. A times W1 is in W1. So every vector in W, well, actually, I kind of did it wrong. If U is in W1, I meant to say this. That implies that 1 times U plus 0 times any vector in W2. So I took a multiple of something in W1 plus a multiple of something in W2, and I get something in W1 plus W2. And this is U. This messes U. U is in W1 plus W2. Okay, but that's a whole nother story. Okay, so let us show that AU plus BB is in W1 plus W2. Okay, but of course, I'm being completely off the wall by using A and B again. We'll say that I erased all the A's and B's and nothing erased. Okay. So how about we say R and S? And V is R prime W1 plus S prime W2. Now, so A times U will be A times this. That is, it will be AR W1 plus AS W2. And B times V times this will be BR prime W1 plus BS prime W2. Okay. So now, AU plus BV, it'll be this number of W1s. It'll be AR plus BR times W1 plus this number of W2s. That's scalar, I should say that's scalar, times W2. Well, this is a real number times W1 plus this is a real number times W2. So yeah, this is in W1 plus W2. Therefore, W1 plus W2 is a subspace of V. So if you have two subspaces of V, if you add these two subspaces, you have another subspace of V. So now you have a way of not only finding subspaces, but adding subspaces. If you add subspaces, you'll get another. If you add subspaces of V, you'll end up with the subspace of V. So I just want to make one last comment on something I just said, that if you have two subspaces of V and you add them together, then you get another subspace. Okay, so let V equal to x1, x2, up to xn be a vector space. Pick xr and xs from V. R is not S, okay? Pick two elements from here. Define W1 to be the set of all scalar multiples of xr. Why don't we call it W sub r? It equals to all scalars of x sub r. C is a real number. And define W sub s to be all scalar multiples of x sub s. By the last theorem, we can then say that WR plus WS is a subspace of V. Now, this here is one set. This is one set. Now, if T is not an element of R S, that is, T is different from R and S, then XT is a subspace of V. And if we think of this as one set, one subspace, which it is, when I add another subspace, this is also a subspace of V. So this addition, it just, V has a lot of elements, my goodness. This gives us a lot of subsets. X1 is a subset, X1 plus X2 is a subset, subspace, X1 plus X3 is a subspace, X1 plus X4 is a subspace, all the way down to X1 plus XK is a subspace. So then you can have just X2. I already said 1 plus 2, but I can say X2 plus X3, X2 plus X4, all the way down to X2 plus XK. And then you can have X3 by itself, or you can have X3 plus X1, which I have, or X3 plus X2, which I already have. So how about X3 plus X4? All the way down to X3 plus XK. All the way down to XK minus 1 plus XK. There are a lot of them. There's a lot of them. Okay, there's an all, well, maybe not. I mean, if n was 2, then I would just have those 3. But if n is a bit larger, like 10 or even 5, goes through the roof. There's a lot of them. There's an awful lot of them. There's an awful lot of them. Okay, that completes this section on subspaces.